Alrighty, welcome back to Fun Maths. Today we're looking at Bernoulli sequences and the binomial probability distribution. So what you do need to know is the following. Let's say you consider a coin toss. You know that there's two possibilities. You can either get a heads or a tails. When you roll a dice, for example, the two possible outcomes for a random variable of interest in that experiment is you could either roll a 6 or not roll a 6. So if we consider a Bernoulli sequence, it's going to have the following properties. Each trial is one of two outcomes, which are either designated or usually designated as either a success or a failure, S or F. The other thing that makes up a Bernoulli sequence is the probability of success on a single trial is denoted with a P, and that's consistent for all trials. And therefore, the probability of a failure on a single trial is 1 take away P. Last thing with the Bernoulli sequence is that the trials are independent, and that means that no outcome, or the outcome of any trial is not affected by the outcome of any previous trials. So let's have a look at example number 1. It says here, suppose that a netball player has a probability of 1 in 3 or a third of scoring a goal each time she attempts a goal. She's repeatedly shot for the goal, perfect. They're asking, is this a Bernoulli sequence? So we need to consider each of those 3 dot points that we spoke about just a minute ago to verify whether or not it is a Bernoulli sequence. So in this particular example, when she's shooting for a goal, it's going to be one of two outcomes. It's either going to be a goal or a miss, that is a success, or a failure. So it does meet this one here. The probability of scoring a goal, which is 1 in 3, is consistent for all attempts, as the probability of a miss is 2/3, or 1 takeaway the probability. So 1 takeaway 1/3 is the 2/3. So it meets this dot point. Lastly, the trials are independent of each other, so the outcome of any trial is not affected by the outcome of any previous trial. So when she shoots for a goal, it's not affected by the previous attempts. So in this particular case, whether they're asking whether this is an example of a Bernoulli sequence, in this particular case, it could be considered a Bernoulli sequence. Alrighty, with binomial probability distribution, what this is about is it's the number of successes in a Bernoulli sequence of n trials, and that's called a binomial random variable, and it's said to have a binomial probability distribution. Perfect. Now there is a formula for this, and it's listed here. It says if the random variable x is the number of successes in n independent trials, each with probability of success p, then x has a binomial distribution, and the rule is as follows. Now notice here we've got n is how many independent trials there are, we've got p, the probability of success, and then also built into that is the probability of failure, which is 1 takeaway p. So let's have a look at how this gets put into action here. It says, find the probability of obtaining exactly 3 heads when a fair coin is tossed 7 times, correct to 4 decimal places. Alright, so what you need to know here is obtaining a head is considered a success here, and the probability of success in each of those 7 independent trials is 0.5. You've got half a chance of getting heads, half a chance of getting tails. So the probability of success, or P, is 0.5. So we're going to let x be the number of heads obtained. In this particular case, they're looking for exactly 3 heads to be obtained. And we've got n trials, so because it's tossed 7 times, n is 7 and p is 0.5. So plugging these things into the formula, obviously we've got n here, we've got x here, p to the power of x, and then it's multiplied by 1 takeaway the p-value to the power of n takeaway x. Yep. Running that calculation, we get 0.273 3, 4 correct to 4 decimal places. Now, the good news as well is you can do this on your ClassPad calculator. To do this, what you would do is you'd go to the main section. So the main section, when the calculator thinks about it. Alrighty, so we're in the main section. Perfect. We're going to go to interactive, and from here we're going to go to distribution. We're going to go to discrete, and from here we're going to go to binomial PDF. Perfect. Now here you'll notice where we can put in the x value, the number of trials, and the p value. So from our example here, the x value was 3, because we're looking at the probability of obtaining exactly 3 heads. Number of trials we did was 7, and the probability of success was 0.5. So using this functionality, binomial PDF, we can click OK, and it will run that calculation for us, which is listed there. Perfect. Alrighty, the next example says here, the probability that a person currently in prison has ever been imprisoned before is 0.72. It says find the probability that of 5 prisoners chosen at random, at least 3 have been imprisoned before. Again, they're asking for the answer correct to 4 decimal places. So if we were just thinking about x being the number of prisoners who have been in prison before, then this here is going to be the formula for that. Obviously, we're choosing 5 at random. The probability that they have been in prison before is 0.72, and obviously 1 take away the probability of them being imprisoned. 1 take away 0.72 is 0.28. We're plugging those values obviously into the formula there. Now, again, the next part of this is we're looking at choosing at least 3 to see if they've been in prison before. So in this particular case, the probability of x, the value of x that we're looking for, is going to be greater than or equal to 3. So what we're going to do to work out the probability of x being greater than or equal to 3, you need to find the probability of it being equal to 3, equal to 4, and equal to 5. And once we get the probability of each of those, we're going to add them together. So the good news is we'd worked out, like generally, how we're going to do that above here. So to work out the probability of x being equal to 3, where x is, we're going to plug in obviously the 3 into here, and we can get a value. Doing the same for 4, and doing the same for 5. Adding those together, we get 0.8624. Cool. So that's achievable, but it takes a little bit of care. Again, the good news is we can do this on the ClassPad calculator in one sort of step. So to do it on the ClassPad calculator, again you go to interactive, we're going to distribution, we're going to discrete distribution. However, this time we're going to be using binomial CDF. Okay, so with binomial CDF, we're going to be looking at entering in both the lower and upper boundaries for this particular case. And so with this one, because we were looking at probability of there being at least 3 being imprisoned before, we're looking at the probability of x, probability of 4, and probability of 5. So to specify the lower boundary, it's x equals 3. So the lower one we're going to be doing is 3. The upper is 5. Again, the number of trials, we're looking at 5 trials here. N was 5. And putting in the probability of success, in this case it was 0.72. When we click this and run it, good news is the calculator will do that for us. Alright, the last one I want to talk about today is the binomial distribution and conditional probability. So it says here we can use the binomial distribution to solve problems involving conditional probabilities. Here's the example. It says the probability of a netballer scoring a goal is 0.3. Perfect. It says find the probability that out of 6 attempts the netballer scores a goal. So the first one, they're wanting to know that she scores a goal 4 times. So it says here, let x be the number of goals scored, and then the x has a binomial distribution with n being 6, because she had 6 attempts, and the probability of success was 0.3. So scoring 4 times, its probability of x is being equal to 4. Plugging it into the formula here where you've got n and you've got x, p was, as we said, 0.3 to the power of x, which was 4. 1, or the failure is 1 take away p, which is 0.7 in this case, to the power of n take away x, which is 2. Run that calculation and we get this value here. Cool. Next one, it says, hey, find out the probability that out of the 6 attempts netball scores a goal 4 times, given that she scores at least 1 goal. So in this particular case, we're finding out a probability that she scores 4 times, given that she scores at least 1 goal. So it's greater than or equal to 1. So again, from this particular stage here, we know that that is the same as the probability of x equals 4 intersection x greater than or equal to 1 divided by x greater than or equal to 1. From here as well, if you are working out the probability of x being equal to 4 intersection x greater than or equal to 1, that statement is just the same as x being equal to 4. From here, the good news is we worked out what the probability of x equals 4 was in the previous part. We've got that listed there. And then on the bottom line of this fraction here, we've got the probability of x being greater than or equal to 1. Another way of thinking about probability of x being greater than or equal to 1 is really saying it's the same as 1, take away the probability of it being 0. So if we think about what the probability of 0 is, if you put in the values here, the 6 and the 0, the 0.3 to the power of 0, then you'd have the 0.7 to the power of 6, you'd end up just with this here on the bottom line. When we do the division, we get our probability here that she scored a goal 4 times, given that she scored at least 1 goal. It would be 0.0675. Thank you very much for listening up. I hope you have a good day. Bye for now.